If you look here, what you can see is an image that shows water in a variety of states. We see liquid water. There's also solid water shown here in the form of snow. There's even some gaseous water or water vapor in the atmosphere. And as you can see, they all have particles of water moving in different ways and spaced in different ways. And we're going to be looking at that today. Different forms of matter can be identified if enough is known about their properties. Now, properties come in two different types. There are physical properties and there are chemical properties. Physical properties are ones that can be observed or measured without changing the matter's composition, meaning the identity of the substance remains the same as it goes through this change. Chemical properties are ones that describe matter's ability to change into new matter, meaning it has a new composition. Its identity has changed, and it now has different properties after chemical change has taken place. There are many physical properties. As we started this presentation, we saw water in its three different physical forms: solid, liquid, and gas. Technically, there is a fourth form known as plasma as well. So state is one physical property, but there are other ones, such as malleability. Malleability refers to the ability of a material to be rolled or pounded into thin sheets, to be deformed without breaking when it's struck. There's also ductility. This is the ability of material to be drawn out into a wire. So we can see on the left that material is a ductile material, meaning it can be stretched quite a bit before it breaks. But the one on the right, it would break in the center instead. So that would be a brittle substance. Solubility refers to the ability of a material to dissolve in another substance. Now, frequently we work with dissolving things in water. You see that a lot in your everyday life. But water does not have to be the liquid that things get dissolved in. As a matter of fact, you don't even necessarily have to have a liquid at all for something to be soluble, and we'll talk more on that later. What you see pictured here is sugar that's added to water. On the right side of this diagram, we can see we have a sugar solution. We call it a sugar solution because it's not changed chemically. You still have sugar, you still have water, but they are now sugar dissolved in the water, and it does not change its identity. Another physical property is electrical conductance. Some substances will conduct electricity. Steel does conduct electricity, so the light bulb is lit up. But things like wood and glass do not conduct electricity, so the light bulb went off with those, whereas it comes on when steel or copper or some other metal is used to complete the circuit. Other physical properties include magnetism. Some substances are attracted to a magnet. We can see iron filings that are attracted to the ends of these magnets. There's also things that stimulate our senses. Color is an example. Color is a visual stimulus. Some things have a very strong smell or a very distinctive smell. Others may have a specific taste, like lemons. Lemons may taste very sour. Some substances taste very bitter. We don't taste things in a chem lab, but taste is a physical property of substances. In the picture in the center here, we see halite, which is salt in its mineral form. And so that particular crystal would taste salty because it is a giant salt crystal. Another physical property is thermal conductivity. Some substances conduct heat very easily, such as that pan. The main body of the pan is made out of metal because metal is a very good conductor of heat. The handle is made out of plastic around a metal shaft that connects the handle to the pan. This keeps the heat from the pan from being conducted into your hand when you need to pick the pan up. In the winter, if you want to warm up, you frequently buy a hot beverage. Now, if you're wanting it to warm you up from the inside out, you would put it in this styrofoam cup because styrofoam is a really good insulator. It does not conduct thermal heat very well. And so that keeps the heat in the liquid so that it can continue to be warm as you drink it. On the left side over here, we see a man holding a ceramic mug. And ceramics will conduct heat much better, which means that coffee or hot cocoa that he has in that cup is not going to stay warm that long. But he can cup his hands around the cup and absorb heat from the cup to warm his hands. So just remember that the heat then would leave the liquid, and he'd have to drink that pretty fast if he wanted it to be warm while he drank it. As we've seen, all substances have properties that can be used to describe them. These properties can be classified into one of two different types of properties. There are extensive properties and intensive properties. Something that's classified as an extensive property is classified that way because it depends upon how much of a substance is present. More of a substance would have more mass, as an example. So mass would be an extensive property. Other properties, though, do not depend upon how much of a substance you have. It depends only on the identity of the materials in the sample. So intensive properties are what we call any of these properties that do not depend upon the quantity of material that you have. Matter is anything that has mass and takes up space, meaning it has volume. If matter has a uniform and definite composition, it's called a substance, sometimes also referred to as a pure substance. Both mass and volume are extensive properties because each one is affected by the amount of substance that's present. If there's more substance present, it's going to have more mass. It's going to take up a larger volume. Liquid volume is usually measured in liters or milliliters. It can be measured using a variety of pieces of equipment, things such as measuring cups like you use in your kitchen, beakers, graduated cylinders, pipettes, and volumetric flasks. Which one gets used is going to depend upon the precision needed in the measurements. Most liquids do not have a flat surface when they're poured into a container. Rather, they have a curved surface that creates a meniscus at the top of the liquid. And you can see that pictured in this picture in the upper right. That surface curving downward is what we refer to as a meniscus. Most liquids with a meniscus curve downward, as you saw in that picture, but there are a few that curve upward, such as mercury. So it's going to do one of these two things. It's either going to curve downward, looking like it's climbing the sides of the container, or it's going to curve upward like it's trying to pull away from the sides. When measuring volume in any of these containers, you always want to read the volume of a liquid at the flattest part of the meniscus. As mentioned before, that's usually going to be the bottom of it, unless you're dealing with mercury. Your line of sight is going to be very important when reading the volume. As this diagram shows, you want to have your eyes at the same level as the meniscus. You don't want to be looking down at it or up at it. That will give you a false reading. Now, measuring solid volumes, when we measure those, we use a different type of unit. We don't use liters and milliliters for solids. We express their units in cubic units, such as cubic centimeters or cubic meters if it's a large volume, like the volume of a pool. The volume of a cube or rectangular prism is found using the formula volume is equal to length times width times height. If we have an object that is not easily described geometrically, we can use a method known as the displacement method to figure out its volume. As shown in this picture, we see a water level of about 20 milliliters on the left. We then take our object and submerge it in the water, and once it's completely under the water level, notice that the water level rises 3 milliliters, from 20 to 23 milliliters. That means it has displaced 3 milliliters of water, so it must take up 3 milliliters of volume. Each milliliter of water takes up a cubic centimeter of space, so we can actually change from a liquid volume unit into a solid volume unit by using this equality. 1 milliliter equals 1 cubic centimeter. So since this is a solid object, we would want to report its volume as a solid volume unit using this cubic centimeters. So we would report it as 3 cubic centimeters, not 3 milliliters. What is mass? Well, mass is a measure of the amount of matter in an object. It usually is measured in kilograms if it's a larger quantity, or grams if it's smaller, or even milligrams. It all depends upon how massive the object is. We can measure mass using a balance like the triple beam balance that we see here. A mass is placed on the pan and the weights are moved to the side and a reading is taken to show how much mass that sample has. Now, those were extensive properties that we've been talking about with mass and volume. Remember that intensive properties do not depend upon the size or on the amount of sample. Some examples of intensive properties include malleability and ductility, color and hardness, conductance of heat or electricity, density, which we will discuss further in Chapter 3, but density is an intensive property, and melting point and boiling point. Now we get to the heart of chemistry, matter. All matter is made up of tiny particles, and we call those tiny particles atoms. They cannot be seen using visible light. We cannot use a normal visible light microscope like you're used to seeing in your classes to view an atom. They are just too small. Atoms can exist by themselves or may be put together to form molecules, such as the water molecules and the carbon dioxide molecules pictured here. These tiny particles of matter are in constant motion and can interact with one another, and that affects their state of matter. There are three basic states of matter, as I mentioned earlier in this presentation. They are, of course, solid, liquid, and gas. And as you view this image, you can tell that these particles are spaced differently between the gas, the liquid, and the solid phases. Now we're ready to focus on solids. What does it take to be classified as a solid? Well, it needs to have constant volume. It also needs to have a definite shape. Both of these are obvious in the picture of the solid in the jar. We can see that it has a definite shape, in this case more of a cubical shape, and it has a constant volume. It's not changing how much space it takes up. Particles are also vibrating about fixed points. In the upper image, it's kind of hard to tell that those particles are moving. In the bottom image, they're trying to show those particles vibrating in place. Particles are also closely packed together, as seen in both of these diagrams, which allows more attraction between the particles. Many solids are classified as crystalline. Crystalline solids have particles arranged in a regular repeating pattern. Now that regular repeating pattern is called a crystalline lattice, and three different crystalline lattices are shown in the diagram here at the bottom. Now I'm not going to expect you to know which elements have a particular crystal lattice structure. I do want you to know that there are a variety of crystalline lattices out there. These crystalline solids have a very specific temperature at which the solid will melt and change to a liquid. Examples of crystalline solids include things such as ice, iron, quartz, and sodium chloride. You can see a definite difference in the macroscopic structure that comes out of the crystalline structure, the way that these particles arrange themselves as they crystallize. Sometimes particles of the same type can be arranged into different crystalline structures. When substances can be arranged in different ways like this, they are referred to as allotropes. Now, one very common substance that has a variety of allotropes is carbon. Carbon can crystallize into diamond. That's pure carbon, but as you can see here, the carbon atoms are connected to four other carbon atoms arranged in a variety of directions around a central one. And it's a very hard crystalline structure there because of all those multiple connections. Graphite is also pure carbon, but as you can see here, the carbon atoms are actually being connected in thin sheets. And so in graphite, the reason it makes such an excellent writing material is that those thin sheets will slide right off the tip of your pencil and be deposited upon the paper or the surface across which you drag the pencil tip. And so that makes graphite a really good substance for writing and for lubricating materials and such because it glides right off. Then there's Buckminster fullerene. It's found in soot. This is what we refer to as a buckyball. There are a variety of different crystalline structures, different ways in which carbon can connect to form bucky tubes as well as buckyballs, etc. Solids may also be classified as being amorphous, and that happens if the particles lack an ordered internal structure, meaning the particles are random. Now, they're held firmly in place, they are not moving around, sliding past each other or anything like that, but they don't have a definite crystalline structure. They're more disorganized. All of these solids are amorphous solids that are pictured here. Examples such as rubber, plastic, asphalt, chocolate, taffy, wax, and even glass. These solids do not melt at a specific temperature. As you may have experienced with holding chocolate in your hand, it doesn't go instantly from solid to liquid like an ice cube does. It will gradually soften over a range of temperatures before it becomes a liquid. Now, in a solid, particles behave in a particular fashion. Here we see solids at the macroscopic level. We have ice. If we zoom in more closely, magnify it 10 times magnification, we can see that there's more of a crystalline nature to the solid. If we magnify it even further, much more magnification, get down to the level of molecules, we can see the water molecules regularly arranged in kind of a hexagonal pattern and vibrating in place.